Okay, so spectral data in the sedimentary deposits of Mars. So in these next 30 minutes, I'm going to tell you about the general mineralogy of the Martian surface and of sedimentary deposits. And then we will focus on the instruments that we can use to probe the composition of the surface, and especially I will focus on CRISM instrument and its data products, because some of you will have CRISM data in the mapping exercise. Okay, so the first thing that one notices when looking at the surface of Mars is, of course, this red color. And this is due to the presence of dust. So dust is almost everywhere on the surface and is made of mainly nanophase ferric oxides. But there are some areas on the surface of Mars that are dustier than others. So as you can see from these two images, the brighter areas of Mars are also the dustier ones, while instead the darker areas are not so dust covered. So dust has an impact on the observation because it obscures the large portion of the planet and prevents the surface from further probing by remote sensing. So when the dust layer is too thick, we cannot see anything other than the dust. But of course, where we see the surface, we can tell then Mars has a primary igneous crust, which is made of mainly plagioclase and pyroxenes, and also some olivine. And on this crust, we have several minerals that derive from secondary processes, such as oxidation, weathering, and interaction with liquid water. And these are, for example, phyllosilicates, which are a type of clay, sulfates, carbonates, and oxides. So the hydrated minerals, so that are minerals that form in by interaction with liquid water, are particularly important because they indicate that Mars had once a past environment that could have been suitable for life, because along with morphological evidence, they indicate widespread aqueous alteration on the surface, and of course their variety also indicates that these aqueous environments have varied both spatially and temporally. And for example, we have flavial-lacustrine environment or playas and groundwater. Here you have a map of all the hydrated minerals on the Martian surface. So we have phyllosilicates, other type of silica, chlorides, carbonates, and sulfates. So the majority of these hydrated minerals is concentrated in two Martian epochs, the Noachian and the Hesperian. So the Noachian epoch goes from 4.1 to 3.7 billion years ago, and it is thought that during this period Mars had warm and wet climate, so with a thick atmosphere and so water on the surface. And the mineralogy reflects the conditions of the environment. So the dominant alteration mineralogy of this period are clays. Then to start going towards the experience, the environment started to become drier and more acidic and increasingly water limited. So we now also have sulfates that appear on Hesperian surfaces. And after that, in the Amazonian, which goes from 3 billion years ago to today, we no longer have any evidence for hydrated mineralogy, and we have mainly oxides instead. So also the sedimentary environments of Mars have changed during the epochs. And here I put some example of water-related sedimentary environments. So while during the Noachian, we have, for example, valley networks and then lakes, crater lakes, and river delta, as you also have seen from the presentation of Monica. During the Hesperian, since the environment started to become more water limited, we no longer have these features, but we have, for example, outflow channels that are indicative of violent floods, sudden water discharges, but they were more episodical. So the dominant alteration mineralogy of the water-related sedimentary environments are clay minerals, for example, smectites, rich in iron, magnesium, or rich in aluminum, or sulfates, and also chlorides and carbonates. One thing that I wanted to mention is that actually carbonates are an expected weathering product when you have a CO2-rich atmosphere and the presence of abundant surface water. However, they are not as common on Mars. So that's something that's still a puzzle. And there are many possibilities to explain that. So some might be that maybe there was not enough water on the surface, or that maybe it was not present long enough. However, this is still debated and could possibly challenge some of the things we said before about the general environment during the epochs of Mars. Okay, so we'll now move to talk about what instruments we can use to probe the composition of the Martian surface from orbit. Here I've listed 4. And we have the first one, which is the TESS spectrometer onboard Mars Global Surveyor. And then the other 3, which are still operating today, are the THEMIS spectrometer onboard Mars Odyssey, and Omega and CRISM spectrometers, which are respectively onboard Mars Express and Mars Reconnaissance Orbiter. So this instrument can be grouped in 2, because the first 2, there are different technologies. So the first 2 are based on the study of the thermal infrared part of the spectrum, while the other 2 are based on visible and near infrared reflectance spectroscopy. So the Omega and CRISM study the light diffused by the Martian surface in the wavelength range from about 0.4 microns to 5 microns, while instead the thermal infrared spectrometers investigate the wavelengths starting from 6 microns and going onwards. So we'll focus on visible and near infrared reflectance spectroscopy because the range, as I said, the range from 0.4 to 5 microns is important because it retains the key features of most of the primary and secondary minerals of the Martian surface that we have seen. So we have, for example, primary igneous minerals such as olivine and pyroxene, which have some assorption in this range, and also sulfate minerals, clay minerals, and ferric secondary minerals. So every type of mineral has its own spectrum with different absorption, different bands at different wavelengths. So this spectrum is a unique fingerprint of that mineral. So if we get a spectrum from for example, CRISM spectrometer, and then we compare that spectrum with a laboratory spectrum, and if they match, we can conclude that we are observing the same minerals. So I'll talk specifically about CRISM and not Omega, because CRISM has a higher spatial resolution and is able to characterize also small-scale deposits with unprecedented detail. So here's CRISM instrument, and basically the light comes in from a telescope, and then the beam is split into two. One beam of light will go on the visible near-infrared sensor, and the other one will go on the infrared sensor after, of course, being dispersed by the grating. So the visible near-infrared sensor covers from 0.4 to 1 micron, and the infrared sensor covers from 1 to 4 microns. But of course, then the final spectrum can be, the two parts can be put together, and we get the final spectrum. So here are the science objectives of CRISM. So the first one is to find new targets of interest, for example, aqueous deposit or something related to crustal composition. The second science objective is to provide information on the seasonal variation of some aerosols of CO2 or H2O and ICES. While the third one is to measure the surface targets of interest with a high spatial and spectral resolution, and we'll see how much high this resolution is. So in order to do that, CRISM has 3 observation modes. So the first one, the atmospheric observation mode, is related to the second, I'll go back for a moment, to the second science objective. So since it's not really related to the surface, I will not talk about that in this case. So we'll go directly to the targeted and hyperspectral observation mode. So in this mode, CRISM is able to acquire images of the surface with a spatial resolution up to 18 meters per pixel, and with using 544 channels across the wavelength range that we've seen before is from 0.4 to 4 microns. So we have 544 colors in this range. And here are the typical products of the targeted observation. So as you can see, the scale is small, and they have this peculiar hourglass shape, which depends on how the image is acquired. Another interesting mode is the multispectral mode. So with this mode, CRISM is able to acquire images at a spatial resolution of up to 100 meters per pixel, and it uses up to 262 channels. So this mode is used to characterize bigger deposits, and as you can see, the products are very different because they cover larger scales, and they are long, and they cover longer parts of the surface. So here is a comparison between the resolution of CRISM and that of Omega spectrometer. And as you can see, CRISM has a higher spatial resolution. Here's the same scene as it would be seen by Omega, by CRISM multispectral mode, and by CRISM targeted hyperspectral mode. So Omega is able to characterize only large scale deposits, while CRISM can go into detail and also can differentiate between, it can further differentiate between some phases. Because, for example, here the blue and the green pixel represent different phyllosilicate phases, which are not detected by Omega, but are differentiated by CRISM. So how the data products of CRISM work? So the products are organized in data cubes. So we have 2 dimensions for the image, for the spatial image, and 1 dimension for the wavelength. So what we obtain in the end is that we have an image where every pixel of that image has its own spectrum. And data cubes are quite complex data, and there are many ways to analyze these data products. One of these, which is the most used, is to use summary parameters. So summary parameters are a way to parameterize spectral data. So for example, they can measure the position of some mineral absorption and the strength of the absorption. And the most used of these summary parameters is the band depth. Here you have the mathematical expression. We can also combine these spectral parameters with in an RGB map, which is called cross product. And here its color channel is assigned to one summary parameter. So gross products are useful because they highlight some spectral variation on the surface, which are related to several features of the spectrum. So we might combine the 3 different features to see how they change and how they are distributed on the surface. So here's an example of how gross product work. So here's a CRISM targeted observation. And this first image is just what a visible RGB image. So it combines the reflectance value at red, green, and blue wavelengths, so that you get an image of the surface, how it can be seen by the human eyes. And this other one instead is a MAF gross product, which is a standard gross product that is used for mafic mineralogy. So here we have in the red channel, we have this parameter which detects a feature which is typical of olivine, the broad feature at around 1 micron. And here in green, in the green channel, we have an index for low calcium pyroxene, and in the blue channel, we have an index for high calcium pyroxene. So if we combine that with the RGB color scheme, we obtain this image. And here's how you can interpret this image. So here it says olivine and iron-rich phyllosilicates will appear red. So we expect that in these red areas, we'll have either olivine or iron-rich phyllosilicates. And then it says that low calcium and high calcium pyroxene appear respectively green cyan and blue magenta. So here, for example, we have magenta color. So we expect to have high calcium pyroxene and maybe low calcium pyroxene here in these green areas. Okay, here's another example instead related to hydrated minerals. Here the same image is another place, but here we have the same visible RGB image that I have explained before. And in this case, we have a PFM gross product, which means phyllosilicates with iron and magnesium. So it is meant to highlight the presence of phyllosilicates. And here in the red and green and blue channels, we have other parameters which are related to spectral characteristics of some type of clays. And they can be interpreted in that way. So if we see red and yellow colors, which is not the case, we might have phenite, chloride, or epidote, or carbonates. And if we see cyan colors, we might have iron, magnesium-rich smectites, or a carbonate rich in magnesium. So we expect in these areas to have either iron-rich smectites or carbonate rich in magnesium. Okay, so to sum up the information about the gross products, gross products are very good if you want to quickly get an idea of the mineralogy of the area, as we have seen, and its extension. And one thing that I have not said is that you can also play with different combination of the summary parameters and obtain custom gross products. So instead of having standard gross product as those we have seen in the two examples, you can mix and play with the spectral parameters that you want, and you can obtain custom maps that highlight several spectral characteristics depending on what you choose. However, there are also some downsides. So one thing is that you should always interpret with care these cross products, because they give you an indication of what type of mineralogy is present in the area, but some features might not be unique to a certain mineral. So as we have different minerals that may share one or more spectral features, some of the parameters may not provide therefore sufficient discrimination between these phases. We have seen that we add the index for olivine, that it can also be positive in the case of phyllosilicates rich in iron. So you cannot distinguish based on only that map if we have olivine or if we have phyllosilicates rich in iron. And another thing is that where cross products are good to simplify a complex data like that of CRISM, but we're actually using only 3 channels at a time. So we are combining 3 different spectral characteristics, but we are not taking advantage of the whole spectrum. So this is what I've called a multispectral approach on a hyperspectral data. So they are useful, but sometimes you may simplify maybe too much the data. And so eventually what you need to do is that those products are not sufficient to determine if a certain type of mineralogy is present. So you will eventually need to to extract the spectra to be sure that you have a certain type of mineral in that area. So here are the example from before. And in the example 1, we indeed have olivine. And here's the spectrum of olivine, which has been extracted from this area. And in the second example, instead, we have smectite rich in iron in this area. And here is the spectrum extracted from the scene. And as you can see, these are compared with laboratory spectra of the same mineral, and they have the same absorptions at the same wavelength. Okay, so in conclusion, we have seen that Mars shows a great mineralogical variety. Both we have many primary and many secondary minerals, and these minerals can tell us a lot about its history and evolution. And in particular, the water alteration mineralogy is significant because, of course, it has implication on the habitability of the environment. We have also seen that we can investigate the composition of the surface with reflectance spectroscopy in the visible and near infrared part of the spectrum. And we've seen that CRISM has a very high spatial and spectral resolution and is able to characterize the mineralogy of small-scale deposits with a detail that has never been obtained before. And in the end, we can use summary parameter and cross product to rapidly assess the mineralogy of a CRISM scene, and they can give us an idea of what minerals we have in that area. Of course, then, as I said before, you will eventually have to look at the spectra to be sure. Okay, and here are some references. Okay, thank you.